Okay, so in this lecture, we're going to learn about series. And let's begin with the agenda first. So if we look here, we're obviously going to begin with the definition of a series. And we're going to learn about different types of series there are, which includes arithmetic, geometric, harmonic, and telescoping for now. And for each of these series, we're going to learn how convergence and divergence work within them. And in particular, we're going to talk about some of geometric series and use tests for divergence to determine whether the series is convergent or divergent. So let's begin with the definition of a series. So series is basically a sum of sequences. We already learned what sequences are. And to denote the sum, we use the Greek letter sigma. So we normally write it as sigma. So again, we have a starting point at the bottom and the end point at the top and an, whatever that an happens to be. So next definition is basically how we have each terms added up to the point we can denote it as a sigma, and that just basically is equal to Sn. So let's take a simple look at simple example. If we have sequence like this, then we will write it as an equals 1 over 2 to the nth power. That's sequence, right? But what if we had so all these terms added together instead? Then we're going to write it as Sn is equal to so it's basically just the sigma in front of the sequence form we had. Let's begin with a quick review of pre-calculus, where we learned about the difference between arithmetic and geometric series and sequences. So, as you might recall, arithmetic sequence and series are the ones where you keep adding a common difference to the succeeding terms, and for geometric series, we instead multiply a common ratio to the succeeding terms. So, two simple examples here. The first one is arithmetic, because when n is 1, we are going to get 1 plus 2, which is 3, and then when n is 2, 1 plus 4 is 5, 7, and so on. So what was the common difference? Common difference was 2. For the second example, this is a geometric series because when our n is 1, then it's going to be 4/3, and then when our n is 2, then it's going to be 4/9 and 4/27, and so on. So our common ratio was 1/3 in this case. So let's now look at the geometric series definition and how it's going to work within calculus. So as I said, geometric series will have a common ratio, so we tend to write it as AR n minus 1. And notice that I have n minus 1 power here, but just n power there. They're both considered to be geometric series, so don't worry too much about that as long as we have this common ratio R. And we are particularly interested in what R is because this R is going to tell us the difference between convergence and divergence. When R is less than 1, we're going to say the geometric series is convergent. And when R is greater than or equal to 1, then we're going to say the geometric series is divergent. Why? Because for series, if we have a sum, then we say that that series was convergent. If it was divergent and not converging to the same point, then there was no way that we could have gotten a sum of a series. So, and same logic goes here. We have a geometric series. when can we find the sum for a geometric series? When r is less than 1, because the sum can be written as a1 over 1 minus r, correct? So if we do get a sum, then we are going to say the series is convergent. So that's why r is important here. But when r is greater than or equal to 1, you learned that there is no sum for a geometric series. It's just going to be infinity. And as such, we're not going to get a convergent series, so we say that it's divergent. Okay, so let's learn more about geometric series within calculus concept. So here is tip number 1. If you see a series and it's in the form of geometric series, then you need to recognize that it's a geometric series with a common ratio so that you can just look at the r and determine if it's convergence or divergence. Let's start with example 1. So we have a complicated looking series here, but we have to use algebraic properties to break this down. So first of all, we need to write it as now notice that instead of 2 to the 2nth power, I use the parentheses to use 2 to second power inside the parentheses, because that will just give me 4 instead of this complicated looking thing in the original problem. And even this, we learned that geometric series will have n power, n minus 1 power, n minus 2 power, but this is 1 minus n, which is not in the correct form. So we have to change this by writing this as, so let's write 4n, and then 3 to negative n minus 1. And so notice that I'm just changing the way I write 1 minus n. Parenthesis n minus 1 with the negative in front is basically 1 minus n, but I'm changing the way I write so that I can have n minus 1, which would tell me that it's a geometric series. And let's continue. Anything negative exponent will be a denominator in a fraction, so we have to simplify this as 4n and 3n minus 1. So now we're getting there. And in order to further simplify, I need to either change 4n so that the n becomes n minus 1, or change 3n minus 1 so that the 3n minus 1 becomes n. Now, it's always easier to change the bigger one and write it as 4 times 4n minus 1. Again, the top ones are same thing. I'm just changing the way I write this. And as you can see, they both have the common exponent. So let's write it as 4 times 4 to the 3 n minus 1. So now we have a geometric series with a common ratio. So r is 4 over 3. And it is way bigger than 1. So we are going to say that it's divergent by geometric series test.